the lecture today on the so last time I finished the strong Markov property. Let me still in the section 1.3, part 2, following terminology, recurrent and transient states. Right. Let me start off with the definition. So given a state X, then part 1, X is called a recurrent state if I start from X, then for sure I will return back X, row X is equal to 1. That means, just in case, this is probability of starting from X, and we'll return the X in finite time. Okay. So for sure, if I know for sure I will return the X in finite time, then I'm gonna call X a recurrent state. The word recurrent already tells you the meaning of X. All right. And if this probability is not equal to 1, then I'm gonna call it transient. So X is called transient if a row of XX is the row XX is strictly less than 1. In other words, there is a chance, so I should say maybe just another word, the probability of starting from X, I will never return the X. Of course, this is 1 minus row XX, right? This is, if this guy is less than 1, then the whole difference is positive. So there is a positive chance I will drift away from X, never returning to X. I'm gonna call X in that situation being a transient state. Let me give an example to illustrate how we determine recurrent and transient example. Let me go back to the gambler ruin. Gambler ruin. Here, assuming I only have up to say 5 states, only from 0, 1, 2 up to 4, say. So I have to stop the game either at the $0 or only 4. Then I get up to $4. So I have, this is what this is 1, 0, 0, 0, 0. And I have 1 here. I have 0.6, 0.4, 0.6, 4, 0.6, 4, 1. Right. Okay. Of course, the rest is 0. So anyway, so the claim that I want to say here is state 0 is recurrent. Okay. Similarly, state number 4 is recurrent. The other 3 guys are transient. Right. So how do we really say, how do we use the definition to show say 0 is recurrent? Okay. What claim number 1 is 0 and 4 are recurrent. And The three guys in 1, 2, and 3 are transient. So let me give a quick sketch of the proof. Actually, not that much difficult. So y0 is recurrent. Suppose if I start at 0. Suppose if I start at 0, then I'm going to stay at 0 forever, right? That means it is recurrent. So how do we really write it down in terms of math? So we observe the following. Event. Say x1 is equal to 0. Of course, if in the step number 1 I hit 0, that means or that implies t0 has to be finite, obviously, right? If I hit 0 in one step, then t0 is obviously finite. Obviously, that means I already returned to 0. And so implying if in terms of probability, starting from 0, next step is 0 is less than or 0, t0 being finite, right? Of course, because the left event is a subset of the right event, so the probability got to be less than that, for sure. And of course, what is this guy? This probability is equal to 1 based on my my transition matrix. Exactly equal to 1, right? Start from 0, go to 0 with probability 1. And so this probability is bounded from below by 1, implying it has to be 1, right? Because probability is at most 1 anyway. So pretty quickly, we arrive at, if I start from 0, returning to 0 in finite time will occur with probability 1. Right. Okay. Similarly, you can see the reasoning for state number 4 being recurrent is pretty much the same, using the same argument. So to say, so similarly, state 4 is also recurrent. All right. Now, number 2. How do I get, say, state number 1 is transient? So pretty much the same idea here. So I will, because from 1, I could go down to, from 1 here, I could go down to 0 with a 0.6 probability. And at the moment I hit 0, I'm going to stay there forever. That means I will never come back to 1. So again, so the event x1 is equal to 0 does imply I will never go back to $1. Right. And as a consequence, I have probability of starting from $1. The next step hitting 0 is a subset is less than 1, t1 being infinite. And this probability here this probability is 0.6 according to my matrix. In other words, I have probability starting from 1, never returning to 1 is at least 0.6 which is obviously positive. And that is the definition of being transient, right? There is at least a positive chance I never return to one, then I'm gonna call it transient. Just the definition. State one is transient. And similarly for 2 and 3. Right? For example, say from 2, right? From 2, say there is a positive chance in, say, I will go down to 1, and then in the second step, we'll go down to 0, right? And the moment I hit 0, I never go back up. So you know, that will imply 2 is transient. Maybe just let me write down for the sake of completeness, just in case. So for example, if I want to consider number 2, right? So I want to write that this way. So suppose I have the following directory. So x1 is 1 and x2 is 0. This will imply I can never go back to 2 like this, right? If such a directory occurs, then I can never go back up to 2. And as a consequence, probability of starting from 2, the first step hitting 1, second step hitting 0 is less than starting from 2. 2 is infinite, right? So how do you get this probability? The left side probability. What is that probability in 2 steps? What is the left side? Left will be 0.6 squared, right? So basically, because from 2 I go to 1, that means P. So P2 go into 1, and then from 1 it go down to 0. Down to 0, right? And it's just a Chapman-Kolmogorov equation, right? Basically, or I should say this is just a Markov property, and this is 0.6, and the other guy is also 0.6. But in any case, the product has to be positive. In any case, the product is positive, implying there is a positive chance starting from 2, I never go back to 2. That probability is positive, right? Indicating or that 2 is transient. All right. So I guess you can fill in the rest of the argument. But I hope it is clear now. For now, I'm trying to prove this directly based on the definition. Eventually, we will have more, I would say, more advanced tool, I would say, to prove it, in a smart way. There's no need like to do this by hand like this. Another example that I want to discuss, just to illustrate the idea of recurrence, is, I remember the social class, the one from social class. Recalling we have what n is either 1, 2, or 3. 1 is, I believe, that's a lower class, stands for lower class. 2 is the middle, and the 3 stands for upper class. Right. And we have what? So 1, 2, 3, 1, 2, 3. What's that? So I don't remember. Where is mine? Nope. 7, 2, 1. 7, 2, 1. 3, 5, 2, and 2, 4, 4. All right. So the claim now is, for example, I can claim state 3 is recurrent. In other words, starting from 3, starting from the upper class, eventually I have to turn back to, the generation has to turn back to upper class in finite time, for sure. So 3 is recurrent. Okay. So here is a little bit tricky, but we will make use of a very nice lemma that will be employed later on in the course. So let me just down here. So proof here. So what is observation? Observation. Pretty nice observation. Observe that for all, say, state x, probability of x, x1 is equal to 3. If I start from x, either 1, 2, or 3, in the next step, I will hit state 3. Well, so that means you look at this, you look at this column, right? Right. So either it's a 0.1, 0.2, or 0.4, either. But the key here is that the minimum is 0.1, right? It's bounded from below by 0.1. Yeah, right. What does that imply? So in particular, that does imply if I start from any x, t, what t I have, a t3 less than equal to 1 is 0.1, at least. I should have written this probability is bounded from below by the fact that I hit 3 in step number 1, right? And that is bounded from below by 0.1. Pretty clear here, I hope. If I hit 3 in one step, that means the first time hitting 3 has to be bounded, at least in one step, has to be bounded from below by 0.1. All right. Did you see? So it's all about manipulation of events, basically. Manipulation of events. We have, a sequence of events, and we want to analyze the relation between them. So what is the next step here? If this is bounded from below by 1, that means the opposite or the complement. So that does imply from any x, t3 greater than 1. What can I say about that? Less than 0.9, because that guy right there is the complement of this guy. And this is bounded from below. This has to be bounded from above, right? So technically that is equal to x t3 1, and this is already bounded from below, then this guy has to be bounded from above. Yeah. So now there is a small claim here, a small claim. We say using induction. We had the following statement. For all x in my state space, probability of x t3 greater than n is actually less than 0.9 raised to the power n. Okay. This can be seen pretty again, really intuitively based on the Stromer-Markov property. But the thing it has to hold for rods, right? Rods. So this is a state number 3, starting from anywhere here, anywhere in step 0, 1, 2, 3, and so on. So I'm gonna say stay here. I'm gonna hit somewhere in one step, not equal to 3. So this event occurs with probability t3 greater than 1, right? This occurs with probability what? Bounded from by 0.9. And so starting from here, from anywhere, I'm going to move into step number 2. I do not hit 3 as well. Let's say over here, maybe. I jump to here, say. Then this guy, you can think about starting from here. This is the same thing. So I will, this probability, I don't hit 3 in step number 2 is also 0.9. And so on, basically. Not really a straightforward proof, not really. But basically from here you can see keep going on to 3 and so on all the way to n. We have this one. Right. For the proof of this, just allow me just to refer to the lemma in the book to save time. So actually that comes from a big lemma. So we have, let me pull out a lemma, I believe that is the lemma number, which number is that? 1.3. Lemma 1.3 in the textbook. Say, suppose, in general, we have the following. Suppose there exists a alpha between 0 and 1, right? And a state y, what's that? For all state x, the probability of starting from x, ty greater than say k is less than equal to point. So that will be 1 minus alpha. So the keyword here, it has to, this inequality has to hold for all x. All right, that's a keyword. Exactly like this problem right here. What do I know? For all x, k is 1. I go back to 3 in after at least one step. It's bounded from above by 0.9. So like this. right here. Right. So boundary above by 1 minus alpha. All right. Then we have the following statement. The probability of, so then I should say for x, probability starting from x, ty greater than n times k. We have to be bounded from above by alpha to the n. In particular, that does imply state y here gotta be recurrent. In particular, why is that? Why is that? So I should say in particular, state y is recurrent. Why is that? Why state y is recurrent? Suppose we have this inequality. Suppose I accept this. Why does it imply y must be recurrent? You take n to infinity. What happens now? Right, exactly. So that's actually a problem from the homework, actually. So let me, so note here. The event ty being infinity, okay, this is just the intersection of ty greater than k. Just maybe call greater than m, maybe. Right. Yeah. This you can imagine like ty greater than 1 contains ty greater than 2 all the way down, right, all the way down. So it contains ty greater than m, right? And so the limit of this sequence is exactly this guy. You can think about it, right? So maybe let me sketch it out using a diagram, maybe. You can think about it, right? So I have a big set here, ty bigger than 1, right? Inside of that set, I have a smaller set, namely ty bigger than 2, right? Yeah, but inclusion basically keep going. Ty greater than 3. Yeah. So what is the limit here? If I take m to infinity right here. So the intersection of every one of them is exactly the set. Ty is infinite. Yeah. Okay. And so in particular, what does that imply? In particular, that does imply probability of, say, starting from y, ty being infinite is the limit m going to infinity, probably of y, ty greater than n. This is the homework number 1, problem number 5. Okay, yeah. So this is homework 1, problem number 5. All right. And so if I accept this inequality, suppose I have this inequality, then as you can see, because alpha is between 0 and 1. This guy is between 0 and 1. And if I take n to infinity, that goes down to 0. So the limit has to be 0. So that provided probability of y ty greater than what? N times k less than 1 minus alpha to the n, right? I take n to infinity, that goes down to 0. So that goes down to 0 as n goes to infinity, right? In particular, that limit right here basically is 0. And so this is 0. With 0 chance, I drift away from y. That means I have to go back to y for sure. In other words, y is recurrent. Okay. Anyway, so if we accept that lemma, and I guess I would just refer the proof. I would just refer the proof to the textbook. And if we accept that lemma, then from here, we can already conclude state 3 in this particular example. State 3 is recurrent. Conclude directly. Okay. So let me erase here maybe. Let me finish this. I don't want to really leave this like that. So we have that. We have probability of y ty being infinite will be basically less than 0.9 to the n, right? For all n, implying y ty being infinite has to be 0. Worst, probability of y ty being finite is 1, or y is recurrent. Okay, so yeah, and so for that example, we can already conclude state 3 is recurrent. All right, so for the proof here, just take a look at the book. Just see the book for the proof. All right, I wouldn't have enough time to go over everything. Is there any question about the argument of y being recurrent? Do we accept the dilemma? All right. So maybe okay. Let me move on to the next. So similarly, you can prove state 1 and state 2 they are recurrent. So all right. So let me move on. This is a recurrent. Let me check if I still have anything to say in this portion. All right. So I don't have anything left. So let me move on to the last piece of this section, which is actually the most important piece. The most important portion of this section, classification of state. Part 3, classification of states. So basically, if I give you a state space, then using the theory in this portion, you'll be able to tell which state is recurrent and which is transient without really having to go through all these really complicated arguments. We will have theory to determine that. To do that, first, as usual, I would have to start with some definition. So a state X is called to communicate with a state Y. If so I guess I want to denote it by the notation X, arrow pointing to Y. If starting from X, there is a positive chance I will return to Y. X is called communicating with Y if starting from X, there is a positive chance I will visit Y in finite time. Right. There is a small note here. Maybe let me leave that as an exercise. All right. So X communicating with Y if and only if and only if there exists an index and there exists a time index n for some positive n, such that p and x going to y gotta be positive. Right. A little exercise, just a little exercise. But this is pretty, again, always intuitive. Right. If I could go back to y in finite time, then at least for some index, for some time step, and from y starting from x, or starting from x at time 0, I will have to hit y. Okay. Pretty much. And reversely, if this occurs, this event occurs with a positive chance, that does imply back that rho xy has to be positive. Just a little exercise here, not really complicated. So let me mention the following lemma. So this exercise, even though it's not really difficult, it's actually very useful. A useful property that we will be using this a lot of time later on. The first lemma small result that I want to mention is if I have the x communicating with y and the y communicating with little z, then x must communicate with z. Right. So what do you think? Should I proceed? Should I proceed? I'm going to use that exercise. That's what I'm going to use, the exercise. X go into Y. Yeah. Yeah. Yeah, that's wording though. How would you write down in math using that exercise? So, well, I guess just let me draw a picture here. And you will see it. So this is X, Y, and then this is Z, right? So if I have X communicating with Y, that means there gotta be a time step, and just that this probability is positive. So I got to go to Y in step, say a step, in N step. Start from 0, right? Here, but at this time, I gotta hit, right? For some N here. So there exists an N, just that the Pnxy is positive. All right. Similarly, if Y could go to Z, communicate with Z, that means there gotta be some other, say, index called M, all right? Or maybe let me call that to be, say, K, maybe. Starting from here, because this is a Markov chain. Starting from here, forget the past. Starting from here, I will have to hit. So technically that would be N plus K, maybe. Right, so I gotta hit Z in a K step. So keep going right here. Right. So here there exists a K, just that P, K, Y, Z is positive. Yeah. And so altogether, if I start from X at time 0, as you can see, there is a positive chance I will hit Z in this number of steps, N plus K. And that is equivalent to saying, according to this exercise, that is equivalent to say X has to communicate with Z. All right. So how do I write down a quick short proof? X communicate with Y is equivalent to saying there exists an N, Pnxy is positive. Now Y going to Z is equivalent to saying there exists K, such that PKYZ is positive. Right. So now, by the Chapman-Kolmogorov, right? Chapman-Kolmogorov equation. Chapman-Kolmogorov equation tells me if I want to go from X, sorry, if I want to go from X to Z in this number of steps and plus K, this can be decomposed into summation on say little u, maybe in S, Pn xu, and then Pk u to Z. Right. In particular, this will be this total sum here gotta be at least this quantity, Pn x going to Y and Pk y going to Z. Right? Because the sum counting every state, and y, little y is one of them. And so that sum gotta be, obviously gotta be divided from below by that product. And I know that product is positive. And so that is positive. And by that little exercise, that does imply X must communicate with little z. Right. indicated with or row XZ. Yeah. All right. Okay, so I only have a kind of like 1 minute left. Let me mention the next definition. Yeah, a lot of terminologies here, unfortunately, a lot to remember. Definition 1, a set C, I guess I want to call it a set A, which is subset of the state space, is called a closed set. All right. If for all state I in A and for all J not in A, I have what P I J is identically 0. This means if a state I belonging to A, I run the chain, I can never get out of A. I can only stay in the set A forever. So that's why A is called closed. Right. All right, so just let me stop here. Yes. So, and continue with that terminology on Monday.